Today we will learn about heating and cooling curves. Our question of the day has three parts. Which heat equation would you use if you were considering a temperature change? Which heat equation would you use if you were considering melting or freezing? And which heat change would you use if you were considering boiling or condensing? Today we will learn about heating and cooling curves. They are used to track kinetic and potential energy changes at a constant pressure. Remember, the average kinetic energy measures how quickly particles are moving and is directly related to temperature. Hot particles are going to move fast and cold particles are going to move slow. Since temperature is the average speed of all the particles in the sample, you're going to have some particles that move really fast and some move really slow. However, the majority of the particles are going to be somewhere in the middle, and once you average all these together, you get your temperature or thermometer reading. Potential energy measures stored energy in a substance or system. The further apart particles are, the more potential energy they have. Gases tend to have the largest amount of potential energy because the particles are the furthest apart. Remember, solids, which are rigidly bound together and can't move a lot, have the lowest potential energy. Liquids have the ability to flow past each other because they have a little bit of space, but they're all still in the same location approximately. And gases have the ability to roam freely, so they have the highest potential energy and are the furthest apart. When looking at a heating or cooling curve, the sloped lines have kinetic energy or temperature changing. During a phase change, the temperature does not change. This occurs when you have a plateau. On the plateau lines, potential energy or the distance between particles is changing instead. Remember, sloped lines have kinetic energy or temperature increasing, and flat lines have endothermic phase changes. The temperature stays the same, but the distance between particles changes. Here is an example of a phase change where you heat up a solid. Notice how from left to right, you start off down here and you have a sloped line going up. Since the temperature or average kinetic energy of the substance is lowest here, we call this a solid. Once the energy reaches this point, it stops going up, and instead we have a plateau. This is because the solid is being changed into a liquid. This is where the process of melting occurs. Once all of the solid has been changed to liquid, we can now start increasing the energy or the temperature of the liquid. And we're going to do that here until we reach this point and switch to a plateau again. At that plateau, we are going from a liquid to a gas, so vaporization occurs. Then we get to this point and we have all gas as the energy starts increasing again. When the temperature of the substance changes, so when we have this solid increasing temperature, the liquid increasing temperature, or the gas increasing temperature, we use the equation Q equals mc delta T because delta T means change in temperature. When going from a solid to a liquid, so melting, we're going to use the heat of fusion because heat of fusion goes from solid to liquid or vice versa. That means that our equation will be Q equals mHF. When we are looking at vaporization, going from liquid to gas, then we're going to use the Q equals mHV, the heat of vaporization. Now, to calculate heat energy changes, remember, when the phase is changing, use equal Q equals mH sub F or Q equals mH sub V. When the temperature is changing, we use Q equals mc delta T. You can add the results of two or more equations together to determine the heat energy change over a longer period. Just like in heating curves, cooling curves have sloped lines that show when kinetic energy changes, in this case when they decrease. And on flat lines, we have phase changes going from one state of matter to another. In this case, they are exothermic because they release heat and the particles get closer together. If we look at this cooling curve, we see that we start off with the highest kinetic energy. The state of matter with the highest kinetic energy is a gas. We then move on to convert that gas into the next state of matter, which is liquid. So from gas to liquid, we call that condensation. Then we're going to get to the end of the plateau and we need to take our liquid and lower its kinetic energy or lower its temperature as much as we can. That's this slope. Then at the end of the slope, we once again plateau out as the liquid is changed into a solid. So from liquid to solid is freezing. Once we have all of our substance frozen or changed into a solid, we can then lower the kinetic energy and temperature of the solid. And that is our heating or cooling curve. Now, once again, we need to consider our equations. So, whenever you have a sloped line, so the solid, liquid, or gas, we are going to use the equation Q equals mc delta T because we are changing the temperature of the substance. The process of freezing takes us between liquid and solid, so we're going to use Q equals m H sub F for heat of fusion. Condensation, the process of taking a gas and turning it into a liquid, uses the heat of vaporization. So Q equals m H sub V. Now pause the video and try the show what you know questions. When you are done, you may resume the video and check your answers. Our first question is, why is the line for boiling or condensing much longer than the line for melting or freezing? Well, the line for boiling and condensing are much longer than the lines for melting and freezing because the particles must move a further distance to change from a liquid to a gas than they do to go from a solid to a liquid.